now we're ready to talk about Kepler's second law of motion. So his first law was that the orbit of a planet going around a star is going to be an ellipse. So his second one is going to be that a planet sweeps out equal areas in equal amounts of time. So let's pretend that a planet is located right here, and then let's say that this represents, I don't know, October. So let's have October to be there. So I'm just making stuff up. And then let's say that this same planet orbits over to here in November. So in 1 month, this thing went from here over to there. Now we could make a line that connects there to there, and then we could connect it from there to there, and then we could fill this thing up with a whole bunch of squares. And then by counting the number of squares and knowing the area of each of the squares, we could figure out the area of this thing. So it's not a triangle, it's called a sector, but it kind of looks like a triangle. All right, now let's let the planet orbit over to here. So now let's say, for the sake of argument, that this is January, and then let's say for the sake of argument that this is February over here. And so again, we could connect it like that, and we could calculate the area that is in here, and lo and behold, this area would be exactly the same as this area over here. Now, how is that possible that that could be? Well, Kepler had absolutely no idea why. He just plotted it, and he noted it, and then he put it in his notes, and then said it's for somebody else to figure out why. Well, it was Sir Isaac Newton that realized it was conservation of angular momentum. So angular momentum is L, and it's going to be equal to the mass of the planet times the speed of the planet times r, where r is going to be the distance that the planet is from the star. So this would represent r, and then v would be whatever speed it would have over here, and then when it's over here, it would have a different speed. Now, notice that this is a large r. The distance from here to here is very large. And then the distance from here to here is very small. Well, if you have a large r, then that would be compensated by a small v. And if you have a small r, then that would be compensated by a large v. So on this side of the star, it's traveling faster than it is over here. So large r, small v, small r, large v. So that's conservation of angular momentum. Well, let's say that you're going at 50 kilometers per hour. Then in 1 hour, you could travel 50 kilometers. Well, if you're going at 100 kilometers per hour, how far could you travel in 1 hour? 100 kilometers. So if you have a big V, then this distance here is also going to be very big. If this V is small, then this distance is going to be very small. And so if you multiply this times this, that's what's going to be giving you this triangle thing. And that's the reason why this one is exactly the same as this one over here. Okay, so that was his second law of motion. So again, let's take a break, and when we come back, let's talk about his third law of motion.